So our next topic is about heating elements and strain gauges and resistance thermometers. So what are heating elements? Basically, heating element is a resistance. It is based on electrical resistance. So when a current passes through any electrical wire, some amount of electrical energy is dissipated as heat energy. So heat energy, and these heating elements are made up of materials which produce more heat. So more input electrical energy is uh, converted into electrical converted into thermal energy or heat energy. According to Joule-Lenz law, Joule-Lenz law, when a current flows through a electrical conductor where when current high flows through it, electrical some because of lattice vibrations and electron collisions, heat is generated. Some amount of electrical energy is converted into thermal energy. So based on his experimental observation, they derived an equation for heat. Heat produced is equal to I squared or T. The generated heat is equal to I squared or T, where I is the current flowing through the conductor for a particular time. So T for time, and R is the resistance. The resistance of the conducting wire or conducting material. I is the electrical current. So this is the basic equation, and from this one can also slightly modify this equation to get power produced. So power equal to quantity of heat divided by time equals to I squared RT. So this equation can also be expressed like this. So heating elements. So there are different types of heating elements. One material which is used in most of the applications is nichrome. Nichrome is a very good acts as a very good heating element because its composition is about nickel. Nickel is about 70% and chromium is about 30%, and it's most of the electrical energy which passes through the nichrome is easily converted into thermal energy. So it is a very good, most of the heating elements are made up of nichrome, starting from electric iron and many other furnaces. All these things are all made up of nichrome. Okay, and here at higher temperatures, when the higher temperature is generated, chromium is converted into chromium oxide, and it makes a outer surface layer on the heating element. So in such a way, any corrosion and any breaking of the core material is prevented. So by means of external uh, insulating layer chromium oxide, the internal breaking as well as internal corrosion and degradation of the materials, all these things are prevented in such a way. Durability of nichrome is very high. Durability or longevity of nichrome is very high because of this highly productive chromium oxide layer. And there is one more material called molybdenum silicide. Molybdenum silicide or it is also a very good heating element which is used in industrial furnaces because of its very high temperature, very high melting point, and also in this case also productive layer based on SiO2 is formed at higher temperature. Silicon dioxide is formed on the surface of the heating element, that is molybdenum silicide. So because of this productive layer, further degradation of the core material as well as corrosion of the core material is prevented. Okay, so in such a way, durability of molybdenum silicide is very high. So mostly it is used in industrial furnaces. So there are many practical day-to-day applications are there based on heating elements. One is, we can say many examples. One is electrical fuse. Electric fuse. And electric iron. Electric iron. Then even incandescent bulb also. Incandescent bulb also uses a heating element. So in the case of incandescent bulb, tungsten filament is used because of its higher melting point, and tungsten filament is used. So more heat is generated inside an incandescent lamp, so that you can realize that you can. And also electric iron. In the case of electric iron, nichrome is used. Nichrome, nickel chromium alloy. For an electric fuse, tin plated copper or tin plated zinc is used. So what is the role of electric fuse in any circuit is, when a higher amount of current flows in the circuit, it acts as a circuit breaker. Because of higher electric current, more heat is generated in the tin plated copper wire. So because of more heat, when it reaches a particular value, it starts to melt because of its low melting point. So it starts to melt, and breakdown takes place, and in such a way it products home appliances as well as gadgets from higher electrical current. Okay, so these are all the various examples of heating element that we use, and now we'll move on to the next topic, strain gauges. So basically strain gauge is here. Strain gauge is a sensor. It is used in a sensor or a transducer. It is used in a main part of sensor or transducer. It is used in used to sensor used as a sensor that is to sense many parameters, many input parameters like pressure, force, or weight. Temperature. So all these things, these basic parameters can be determined precisely by means of using strain gauge. Okay. So the same strain gauge is a part of sensor or your sensing element. Yeah, it is a sensing element. Usually, it is made up of any electrical wire or semiconducting material. So on a flexible plastic sheet, plastic or polymer sheet, yeah, very thin film of metal or semiconductor. Metal or semiconductor is deposited on a plastic sheet, or sometimes this metal or semiconducting thin film may be attached or adhered onto the plastic sheet by means of any glue. Okay. So in alternative way it can be produced. So this part will be connected to any Wheatstone bridge in such a way any input parameters like pressure, change in pressure, change in temperature, as well as change in force or weight can be measured accurately by means of connecting this strain gauge with Wheatstone bridge. Okay, so finally you will get this changing input parameters will modify the electrical resistance, and finally you will get electrical output, that is voltage. So the voltage is a measure of the output voltage that is displaced in the sensor is a direct measure of, or it indirectly gives information about the changing pressure, changing temperature, changing force. Okay. So it is very important in electronics as well as in nanotechnology in making sensors and transducers. So here, what is most important is the length of the wire. If the length of the wire is very high and its thickness is very small means it is moderate, and in this case length is very high. In one case, length is small and a smaller one, and the thickness is also small, moderate. And in another strain gauge, if length is very high and thickness is minimum, means sensitivity for this type of strain gauge will be very high, more sensitivity. And in this case, sensitivity will be comparatively small. So in most of the strain gauges use metals or semiconductors with having very high length and very smaller thickness, very small thickness. Okay, that is aspect ratio must be very high. Aspect ratio, that is surface to volume ratio must be very high. So in such situation you will get more sensitivity, more sensitivity. So what is it? So it is a coil type of strain gauge. It is a coil type of strain gauge. And in a strain gauge, the one parameter is very important, that is gauge factor. Now we will derive an expression for gauge factor. In fact, suppose if you imagine a flexible tube containing mercury. Mercury is a liquid metal, flexible tube, and imagine it acts as a strain gauge. So for any small external force, since it is enclosed in a flexible container, or its geometry changes or it deforms. It means strain. That is, strain is generated. Strain. Okay. Change in length divided by original length. So that is what strain. So because of the external force or pressure variation, this flexible mercury contained in a flexible layer deforms. So this deformation is nothing but strain is generated. Strain is generated, and this strain or deformation changes resistance of mercury. Okay, changes resistance of the mercury. Okay. So for a small change in a small deformation, there must be a correspondingly smaller change in resistance. So let us here resistance play a major role. So resistance is, as you know, it is directly proportional to length of the mercury container, and is inversely proportional to its thickness. So finally, you will get an equation. Resistance is directly proportional to L by D. So R equal to rho into L by D. Rho into L by D. Here rho is the specific to that particular material. It is characteristic of resistivity. It is characteristic of the particular material. Okay. Whereas resistance depends on the deformation or geometry of the material. At the same time, resistivity depends on the nature of the material or type of the material. Okay. Then, so we want, I'm going to derive an expression connecting strain and resistance. So for that I'm going to do some modifications like rho into L by D into, I am going to multiply and divide it by L. So R equal to rho into L squared by D L. Now I am going to differentiate. So dr by dl equal to rho into 2l divided by dl. Again I am going to multiply and so here dl is nothing but density. dl is nothing but the product, thickness and length will give volume. Okay, it is a volume. D into L is volume of this container. So I am going to replace, instead of dl I am going to write it as rho, not rho, it is volume divided by volume. So dr by dl equal to rho into, again I am going to multiply it with L, 2L into L divided by VL, rho 2L square divided by VL. L square by V. You call it as equation number 1. So you can substitute equation 1, that is instead of rho L squared by V, instead of rho L squared by V, you can write it as a R, simply as R. So dr by dl equal to instead of rho L squared by V, I am going to write it as R. And 2 and 2 remains there, 2 R divided by L. So dr by R equal to 2 into dl by L. So change in resistance. This is the change in resistance and it is original resistance. So dr by R equal to 2 into strain. Here dl by L is nothing but strain. Okay. So alternatively it can be written like this: dr by R divided by strain equal to 2. So change in resistance, the ratio between change in resistance and length and strain is about 2. So here 2 is called gauge factor. It is in short it is mentioned as K. K is a gauge factor. So for mercury, the value of gauge factor is exactly 2. For mercury it is 2. For other materials, other metallic materials and other semiconducting materials, it will be different. So based on the gauge factor magnitude, we can tell the sensitivity of the particular strain gauge. Okay. So here dl by L is nothing but strain, epsilon. So for metals and semiconductors, the value of strain gauge is different, and mostly for metals, the strain gauge value will be from, that is gauge factor value will be from 2 to 3. 2 to 3. The value of gauge factor. For metals, its value will be around 2 to 3. For semiconductors, it will be from 100 to 170. The value of gauge factor K is varies from, it means sensitivity. When a strain gauge, semiconductors are used as strain gauge, then sensitivity will be very high. Mostly in the case of metals, an alloy constantan is used. The case of metals, constantan is used as a strain gauge, and for semiconductors, silicon based alloys or some impurities are doped into silicon to improve the strain gauge, to improve its sensing ability or gauge factor. So strain gauges are used as a sensors or transducers. Sensors or transducers. So for that you have to use a Wheatstone bridge. So one arm of strain gauge will be connected to the Wheatstone bridge, and finally you can calibrate any changing input values starting from pressure, temperature and force. So you can calibrate different values of input to the corresponding output electrical signal, that is voltage. It's an indirect way of measuring the changing values of pressure, temperature, force or weight. So the next one is resistance thermometers. Resistance thermometers. One can classify resistance thermometers into 2 types. One is metallic thermometers, and second one is semiconductor thermometers. Semiconducting thermometers. As you all very well know, that the case of metallic metals behave, TCR is positive, positive. Temperature coefficient of resistance is positive. It means when temperature increases, resistance also increases. For semiconductors, reverse or opposite. TCR is negative. Temperature coefficient of resistance is, that is, temperature increases means resistance decreases. So it is negative. So these metallic and semiconducting thermometers are used in different places, starting from microwave ovens to furnaces, okay, high temperature furnace and low temperature furnace, and even in many automobile engines to monitor varying temperature. These thermometers are only basically used, and these thermometers have many advantages as well as demerits comparatively. So I will tell you one by one. First, let us start with metallic thermometers. In the case of metallic thermometer, usually there is there will be usually a ceramic tube on a ceramic tube. Metal is wound on the ceramic tube and two terminals, and it will be placed inside a